Hey everybody, this is Scott from the ThreeFold team, here today with an informational presentation on full VMs, micro VMs, and containers. We're going to talk about how these three technologies are at play on the grid and how you can use each of them in deployments and what some of the advantages and quirks are when using full VMs and micro VMs on the grid. This won't be a demo, so I won't be showing you how to do any of this stuff. We're just talking about the concepts, some history, and just giving some knowledge that you can use as you move forward with using the grid and creating deployments. I'm going to be covering the concepts here briefly. So if you have some experience with VMs and containers, hopefully I won't bore you too much and maybe give you some interesting tidbits you didn't know. If you don't know much about these concepts or are kind of fresh to working with this stuff, hopefully this will give you some foundational knowledge. Bits and bytes for today, we're going to understand what are VMs, containers, and some history. We're going to look inside VM and container images, see what's in there and how they differ. We're going to step through the deployment flow on the grid, so how micro VMs and full VMs come to be on the grid, and then again the quirks and advantages of working with each type. What are VMs and what are containers? These are both abstraction layers for compute. So these are ways that we can create an execution environment to execute applications. In the case of VMs, they're managed by a hypervisor. In the case of containers, they're managed by an orchestrator. So we have some software. In case of a hypervisor, this could be running directly on the bare metal, and the virtual machines be running on top of that, or the hypervisor can be running inside of a host operating system. In the case of an orchestrator for containers, we always have a host operating system. So these are two different types of managers for each type, VMs and containers, that, again, create this environment within which we can execute applications. In the case of a VM, this gives us a full operating system and allows multiple operating systems to run on the same hardware. So this could be like running Windows inside of Mac OS or running Linux inside of Windows, things like that. Or again, it could be running multiple copies of Linux next to each other on top of a hypervisor. And that's the case with ZeroS. This is, like I was saying earlier, like a bare metal hypervisor. So it runs directly on the hardware, and its only job is to provision and manage virtual machines. Now, containers run multiple environments within a single operating system, a shared kernel. So a container contains everything that an application or a set of applications needs to run, all the supporting software, and it runs in an isolated environment. And multiple containers will share the same kernel that's provided by the host operating system. A kernel is just the interface between the hardware and the software in a computer system. It's kind of like the first program that starts up when you start the computer, and it provides an interface for the operating system and the applications that you might start up within your operating system to talk with the hardware to get input and output from the hardware devices in the system. And the resting state for either a VM or a container is known as an image. So this is files plus metadata. We'll talk about this a little bit more later, but basically when you think about a VM or a container, you can think about it like a folder on the computer that's got some files within it and potentially also some metadata. We'll see what that metadata is and how it's used later. And a compute deployment, when we talk about the ThreeFold Grid and the kind of deployments that you can create, our virtual machines, our Z machine is the compute primitive on the grid, and so when you take this image and execute it, that becomes a compute deployment. That's the execution state of an image, which is the resting state a virtual machine or a container. All right, that's a lot of information. Let's check it out in a visual format with some rectangular prisms here. On the left, we have VMs. So again, at the bottom, we have the hardware. Running on top of that is a hypervisor, which could be running within a host OS or it could be a bare metal hypervisor. The hypervisor is running one or more VMs here. In this case, we have two. Each VM has its own kernel. These things could be packed together. But just for the sake of demonstration, we'll show the kernel as a separate bit here. And then each VM has a couple of apps running inside of it. And these things are fully isolated from the kernel level all the way down to the hypervisor, which is providing a shared interface to the hardware for each VM. In the case of containers, again, we have our underlying hardware. We have, in this case, our host operating system, which is running a single kernel. And we also have some kind of orchestrator that is running these containers. In this case, we have some application containers, and we also have over here a system container. We'll talk later about what the difference is there. System container is kind of more like a VM, but these share the same structure. They rely on the underlying kernel provided by the host OS, and they have a bit less separation, as we can see, than the VMs on the other side. So brief history of VMs and containers. Both have their roots in technology that was developed originally in the 50s and 60s on the old kind of mainframe computers that were in use at the time. And the roots of both technologies came out of a move towards multitasking, multiprocessing within the computers at the time. So originally computers just did one thing at a time, and as the engineers working on these computers wanted to start running multiple applications in parallel, it became necessary to develop some new technologies to essentially isolate these different processes, allocate resources to each of them, and those are really the roots of what grew into virtual machines and containers. Of course, modern operating systems can do multitasking without virtual machines or containers, but these are two ways of providing greater separation, isolation, safety, security between essentially just multiple processes running on the same hardware. And the goals as these technologies have developed, and in both cases, the original root technologies kind of faded out, and then there was a resurgence in each case of VMs and containers becoming kind of the technologies that we know today based on those roots. And the goals along the way have been greater portability. So this is the ability to run code on different types of hardware without needing to change it. And especially this was in the late 90s, a desire to run commodity operating systems like Linux, Windows, Unix on specialized hardware. That was the kind of more mainframe style operating system supporting hardware from vendors like IBM and HP. So through virtual machines, you could run Linux, Unix, and Windows on these hardwares that didn't traditionally support them without needing to change the operating systems. And today, there's portability in like Linux apps that are containerized. This is like snaps and flatpaks are a way to run Linux applications on different, within different Linux distributions or different environments without needing to worry about the environment there, the different versions of libraries and things like that. And of course, if you're running Windows applications inside of a VM on your Linux system, that's portability as well. Another goal is security. So this is isolating processes from each other. So if something goes wrong in one process, it doesn't affect other processes running on the same system. And also stopping privilege escalation, which is a way that attackers that are able to attack one application or piece of software running on a system might be able to gain access to other parts of the system that weren't originally available to that application. So this is ways of drawing boundaries around different applications running on the same system to keep them from affecting each other in the case of attacks or just bugs and other problems in software. Also for performance reasons, especially the efficient use of available resources. So both VMs and containers allow people that are responsible for the deployment of applications to take a piece of hardware and stack multiple VMs or multiple containers on top of it in a way that is better able to make use of kind of any spare resources that might be available. In both cases, it provides ways of pooling together multiple hardware systems and treating them like one larger system. So instead of having a lot of small gaps, you're able to spread things over available hardware in an efficient way. And also for multi-tenant systems, the idea here is to be able to limit and monitor the resources used for the purposes of billing. And this is an early kind of push towards the cloud environment that we know today. So when you have multiple customers or multiple users that are sharing the same hardware, both VMs and containers can be a way of limiting the resources that are available to each customer based on what they're paying for, and monitor the use of resources like bandwidth in order to bill them accordingly. So from the late 90s and into the 2000s, VMs were the hot new thing, and businesses that were previously running their servers on bare metal, in many cases, were looking to move to VMs as a way to gain some of these benefits that we saw above. And then from about the 2010s, early 2010s onwards, containers started gaining ground as a popular alternative to VMs for how to package and deploy software. Today, containers and the orchestrator Kubernetes is the dominant compute abstraction that's being used by most businesses and large websites out there today to manage their presence on the web, to manage the applications that they deploy, to support their websites and apps, smartphone apps and things like that. So it's almost certain that you interact with some service that is run on containers and Kubernetes in the background. There's also today an increased interest in small and quick starting VMs, known as Micro VMs, which can leverage container workflows and then deploy the end result as a VM, so kind of getting the best of both worlds. And we support all three paradigms on the grid. We support full VMs, we support micro VMs, and you can use containers directly in Kubernetes or Docker by installing Kubernetes or Docker inside of a full VM or micro VM. And the way this looks in the wild is it's simple. So we have, at the bottom, we have our node hardware. We have 0S as our hypervisor, like we saw in the diagram before. In this case, we're running a micro VM. Inside the micro VM, we have Docker, and Docker is running a container. Now, you might be thinking, this actually doesn't seem simple at all. We have micro VMs, which are based on containers, running Docker, which is a system for managing containers, and then we have this container. Why not just run the container as a micro VM in the first place? And that's a great question. In this case, I'm showing this example because it's actually how some of our solutions are built on the grid, like our pre-search solution, OwnCloud, some others. They're based on container images running inside of Docker, running inside of micro VMs. The reason for this is that a lot of applications these days are providing container images and providing instructions for how to run them in Docker, and a nice tool chain. So in the case of pre-search, they have a way to keep the pre-search container up to date, which is important because nodes that aren't up to date get booted off the network. So by installing Docker in a micro VM, we're able to use the tools and the processes that they provide, Presearch provides, in a straightforward way. Whereas if we're running that container directly in 0S, we'd have to kind of replicate that functionality. And Docker running inside of a micro VM is still relatively lightweight compared to a full VM. So there is some added complexity here, which doesn't strictly need to be there, but it's actually not too bad. And this is nice because, again, a lot of applications out there are providing containerized versions and instructions for running in Docker, and we can do that in a micro VM like this. Now, there's two main types of containers. We saw these earlier. One is application containers, and this could contain as little as a single executable file. So a container in its sort of stripped down base format is just a single executable program that can be run. And application containers are stateless. So if they happen to crash or we expect that they're disposable. So when the container's done, it gets disposed and any changes that were made inside the root file system in the container are lost. In this case, we expect that the data, any data we have, is stored elsewhere in a database or in a volume or disk that's attached to that container. And I'll also say here that application containers, while they could contain as little as a single executable, they're often based on operating system containers that are still really small. So like an Alpine Linux container can be as small as 5 megabytes. An Ubuntu container can be as small as, say, 30 megabytes. So these are very basic operating system collections that are just some tools and the package manager that provide a convenient way for application packagers to get the software that they need into the container to support that application if they need more than just that single executable. There's also system containers, which are one form of VPS or virtual private server that you can rent from some different cloud providers out there. And system containers contain an operating system that could be more or less full-featured and include different kinds of tools and utilities. A system container might run multiple services versus an application container that's designed to run one service. And system containers are stateful. So any changes that we make inside the container, we expect those to be stored if we happen to reboot the container or if the system that container is running on itself happens to reboot that hardware. And any container can become a micro VM as we use them on the grid. And our micro VMs are a bit more like system containers in that they are stateful. Changes you make in the root file system will be stored, but we can also use application container type paradigms. You can attach disks and store the data elsewhere, things like that. Here's a basic example of what a container image might look like. This is a Hello World container that's provided by Docker Project. And in a terminal, I can use Docker run Hello World to run this container. And it's just going to spit out a message that says hello from Docker and some other stuff below. And this container is just a single executable and some JSON metadata. That's all we have in here. And this metadata tells us some things like the command that we should run when we execute this container. So when I run Docker run like I did above, it looks into this metadata and says, okay, I need to run hello, and then it executes the executable. There's also some information in here about the environment. If you have environment variables, a hash that helps us to know that we downloaded a correct and uncorrupted copy of this container. It tells us which operating system it expects to run on, in this case Linux, and some other stuff. So that's all inside of the container image that we would download from the Docker repository hub before we're able to run this image. Now, VMs contain a complete operating system, including the kernel we discussed before. They are stateful, so we expect any changes we make inside of the root file system of the VM to persist if the VM happens to reboot or the hardware it's running on happens to reboot. And VMs are known for providing very good isolation and security because each VM has its own kernel. And historically, this was the focus of development in virtual machines, is prioritizing isolation and security, sometimes at the expense of performance. So VMs tend to be a bit slower to start up, but some modern technologies like we use on the grid, especially for the micro VMs, can be very fast to start up. Here's a typical VM image, and inside we have the image file, which is a file system that contains our normal Linux directories, var, lib, etc., and also important here, a boot directory with a VM linas file, and this is our kernel. So originally this file was just called Linux, and then the VM here actually stands for virtual memory in this case, so it tells us this kernel supports virtual memory. The X changed to a Z to indicate that this is a zipped version of the kernel. But this is just our executable kernel here, and the VM is going to, the hypervisor is going to execute this when it boots up this VM. And then we have thousands of other files that we would find in a normal Linux distribution, and these images, like for Ubuntu, tend to start around 700 megabytes. So that's considerably larger than our 30 megabyte container image for Ubuntu. And that's because they come with a lot more system utilities and a lot more things that you would expect or find, if you're following a tutorial online, it's telling you to type certain commands into your Ubuntu terminal. More of those things are going to be included here by default in the full VM. In this case, we also have a VirtualBox file that's in this directory. And this is not strictly required, and this is one distinction between VMs and containers, is that in this case, our metadata, which is inside this file, is optional. So VMs don't need to have any metadata included, and they're typically distributed as just an image file. But in this case, since I've run this image within VirtualBox on my local system, I have the VirtualBox file, which includes the metadata about how much RAM to allocate to this VM, which disks to attach to it, the networking configuration, and things like that. In the case of the grid, this metadata is going to be specified at deployment time and will either be included in the TF chain contract, so how many resources to allocate, or be sent directly to the VM itself. That's things like the public SSH key that we want to use to log into the VM. That'll be sent to the node itself. So we'll send some metadata to the node, some metadata will be stored on TF chain, and 0S will use both of those data sources when it deploys the VM to create the proper environment based on what resources we're paying for and what SSH key we've specified that we want to use to log in, any disks that we want to attach, and that kind of stuff. Here's that deployment process, both for full VMs and micro VMs. On the bottom, we have the flist hub, which is where we store all of our images for the grid. And on the top, we have 0S running on a node. So in the flist hub, we have all of our different flists, could be PeerTube, could be Mastodon, could be Presearch. And here's Ubuntu, which is kind of a special case because we have both micro and full VM images for Ubuntu. So in that case, we will download the flist into 0S. When someone requests to make a deployment, 0S will download the relevant flist. This could be the micro VM or the full VM image. In the case of a full VM, we're going to do what's known as a firmware boot. So 0S, using its hypervisor, will boot this VM image, essentially emulating hardware. So that's what firmware boot does, is it behaves like hardware, and it uses the image and it becomes full VM. So that's relatively simple. Of course, like we said before, we might attach some disks or anything like that, and we're going to pass in that public SSH key that the deployer provided, and that happens all through this boot process. In the case of a micro VM, our flist is going to have a container image inside, and 0s is going to attach a generic kernel, and it's going to do something here called direct kernel boot. So instead of booting this from an image using hardware emulation, the hypervisor in this case is going to boot up the kernel from the generic kernel provided here, and then it's going to hand that off to the container, and that becomes a micro VM. So that has some consequences. This kernel is not a file that's accessible inside the micro VM. It's just something that gets started up in memory through this direct kernel boot process. For micro VMs, we can use our container workflow and any existing containers as VMs. So this includes a huge library of images that are out there, for example, in the Docker Hub. And container workflows are nice. They're simpler than working with full VM images, and there's kind of a whole ecosystem for how to manage different versions and distribute these images, which is not, at least not built into the world of full VMs and VM images. We are limited in a micro VM by that provided kernel, so we can't replace the kernel and we can't load any modules into that kernel. So if you need a custom kernel, or you need something that's not, if you need to load a module, then this kernel is going to be too limited for you, or the micro VM will be too limited for you, and you should look into a full VM. If you just need basic kernel functionality, then the micro VM should be fine. A container OS is typically not full featured, so the micro VM images that we provide for Ubuntu, they don't have systemd inside, and they don't have a lot of utilities provided by default. Most of that stuff that you can install, and there are container images that have systemd inside, so there's ways of working around this, but typically when you spin up a micro VM, you have just a bare bones set of tools and then your package manager to be able to install more. The root file system of our micro VMs is not a disk, it's a virt.io file system. And this, some users have found, is a bit less performant, and it also means that we can't upgrade our micro VMs in the same way that we can upgrade a full VM. So on the grid, with the concept of an upgrade, basically what you can do is detach the disk from the VM itself, and then attach a new VM with greater resources to that same disk. Since the root file system, the micro VM, is not a disk, there's no way to do that. We can attach a separate disk to store our data, and then we could attach a new micro VM with more resources allocated to it, but any changes that we made to the root file system in that case are going to be lost. Only the data that's stored within the disk will be persistent. And in micro VMs, we can pass environment variables in at runtime. This is something we don't have in full VMs. So this is a typical feature of containers, to be able to pass in environment variables and customize the execution of that container. And we can do that with micro VMs in the same way that you'd expect, by passing those in through the playground or through Terraform. Here's an example on the flist hub of what a micro VM image looks like. In this case, this is our base Ubuntu and the TF official apps folder here. And that's one way that we know that this is a micro VM image, because everything in apps is micro VM, and our full VMs are under official VMs. Also down below for micro VM, we'll see the files and directories that are contained within. In this case, we can see we have this boot directory, but there's no kernel inside, like we discussed earlier. Container images don't come with a kernel, and there's about 2,500 files in here, which is pretty typical for an Ubuntu container image. And our container images are just the base that's provided by Ubuntu, and we installed the SSH server and zinit to start up that SSH server or any other applications that you might want to start in an image that you, in an application that you would use from this base image. But if you just deploy a Ubuntu Micro VM on the grid, you basically get an Ubuntu container with SSH server installed, and that's pretty much it. Now, full VMs, we can modify the kernel. So the kernel is going to be a file within our VM image that we can replace or upgrade. We can also load kernel modules. The root file system is a disk, so we're able to upgrade the full VM and persist any changes that we made to that root file system, any software that we installed, things like that. Full VM images are typically much larger and slower to load over the network. Like we discussed before, we're talking hundreds of megabytes base versus tens of megabytes for container images at base. Containers can get much larger too, of course, depending on what's installed in them. Manipulating images is a bit more complicated. You need to work with a hypervisor, and you have to resize the images. When you're working with containers, the workflows are really nice, and you don't have to worry so much about, say, the size of images or having empty space inside of them, things like this. And for full VMs, we don't have any environment variables or other config beyond those public SSH keys. So 0S will allow us to pass in the public SSH key, and that's for now. There is a tool called Cloud Init, which is typically included in full VM images that are meant for the cloud, and I'm hoping to see support for this so we can pass in additional configuration to our full VMs in a later version of 0S and the grid. But for now, you can customize full VM images, and of course, you can use automated tools to customize them after deployment using SSH. Those are things like Ansible, which will SSH into your VM automatically, install software, do configuration, and things like that. So there are kind of ways around this, but you can't pass any environment variables in. Here's a full VM image, again in the flist hub. And we know because it's under official VMs, and we also know because down below here we only see a single file, image.raw, and that is the file system image that contains all of the files that are part of this full VM. And that's how it looks here. And again, that's going to be a relatively large file because our full VM images tend to include more software. And that's it. Let's review. So on the ThreeFold Grid, our compute primitives are VMs. We have micro VMs, we have full VMs. You can use containers by deploying them as a micro VM or by installing Docker, Kubernetes, or another container system inside of your VM. So again, we support all three of these paradigms on the grid. Our full VMs are a bit more flexible and heavier weight. Our micro VMs are a bit more limited, but they're also lighter. And Z Machine uses ZOS as an orchestrator. So this means that by interfacing with 0S through TF chain and the libraries that we have available, it's possible to develop a lot of cool things maybe that haven't been invented yet using 0S as the orchestrator. And I hope to see some cool stuff around this in the future. I think the combination of micro VMs and some next generation thinking in terms of how these can be orchestrated could be a really cool step forward for the general state of compute abstractions and this kind of timeline that we've been discussing. So I hope that you'll take what you learned today, go and build something cool. Again, my name is Scott from the ThreeFold team. If you have any questions about what we saw in the video today, feel free to hop into our grid testers chat or message me directly. Give me a tag on the forum. I'd love to help you out with whatever you're doing with the grid. All right, until next time, see you later.